This is day 3, the process control day, section B. You have 10 seconds to memorize and review this picture. You have 10 seconds to read this screen. So which of these two provided more information? Which provided it clearer? Which provided it faster? Now read this paragraph in 10 seconds. Once again, I will argue that a picture is more powerful than words. So when we're creating a flow chart, I like to use 3 different objects. One is a rectangle, which would represent a process step. So whether this step is value added or non-value added, it's an operation that we're following. Next would be a decision, and that's in the shape of a diamond, basically a square just rotated 45 degrees. So this is a decision that we're making, whether a job is good or bad, whether it's a type 1 or type 2, or maybe even 3 types of jobs or product that's going through your area that may take 3 different flows. So it's a decision that we get to. And then lastly, we have a connector, and the connector is simply a line with an arrow on one side so that we see the movement of the work going through the area. Process maps should be simple, they should be easy to follow, and kept at a level that's appropriate to the process that you're trying to describe. How do you create a process map? Well, I'm going to tell you the best way to do this is through a process walk and a peer interviewing. So what we're going to do is we're going to walk through the process. We're going to talk to the people that are actually operating the equipment or producing the product or work going through the area, whether it's a office environment and they're processing invoices or requisitions, or they're producing reports. Anything that they're producing, we're going to want to understand what process they're following. So we want to speak to those people, and we're going to map that out as we go through the process. So here are 2 spaghetti diagrams, different types of flow process flow chart, or different way to look at your process. And basically what this looks like, and especially the before, looks like a big plate of spaghetti, and we've got a lot of movement. In this particular case, the product was an order acknowledgement. So this was actually paperwork, and this was the movement of paper and this acknowledgement and associated documentation that was moving through this facility. You can see it went to a lot of different areas, and it, touched a lot of different people. We actually enhanced this flow, moving it from 4 weeks down to less than a week, and eliminated, you can see, hundreds of miles of travel during the course of this year's time that so many of these acknowledgments are processed. So they're processed much quicker. We're getting answers to the customers that much faster, and you can also see that it touched a lot fewer people. A number of the steps that were eliminated obviously were not needed, and then some of the steps that were left were actually done electronically. You can see in the bottom after spaghetti diagram, you can see a dotted line. That was an electronic transfer of information. So that, I believe, went back and forth in that particular case. So cut down a considerable amount of movement, significant amount of time, and when you go to introduce people to these processes in the future, when you train someone, it's so much simpler to train people to a new and enhanced process such as the one on the bottom versus the one on the top. So here is a before and after. These are just two more examples of flowcharts, what they can look like. You can see the different arrows coming off the decisions, and I'm trying to think, where do we have a decision? Okay, on the top before improvement, you can actually see that there are basically four different lines that come off a decision. So the decision says type, if you can make it out. There's a level 1, there's a customer supplied, and there's a level 2 and 3. So it actually goes in 4 different directions coming out. What's really interesting is that the enhanced process still has those, but it's basically the output's been simplified, and the level 2 and 3 actually go to the same spot. Instead of them going to 2 spots, they actually go to 1 spot in the future. So we've simplified the process, but this is just showing you 2 examples of flows. Very easy to review with people, and certainly if you're going to train somebody, you'd much rather train somebody to a process that has fewer steps than one that has many more steps. So we have this as an opportunity to show you a before and after on a process, but again, just 2 more flow charts just to give you some references of what they could potentially look like in your facility. So we're going to talk about a Pareto, and a Pareto basically is going to take our attribute data. This is our categorical data, and we're going to show this in a format that's going to provide us with the largest quantities to the left and the smaller quantities on the right. So the bars that you see rising from the bottom, in this particular case, that says too long, a bad print, wrong revision. These are issues that we had with this particular product. Those bars are rising relative to the axis on the left, which is 0, 100, 200, 300. Those are the number of instances. So too long had approximately, well, we can see from the chart on the bottom, 345 instances. Bad print was 85, wrong rev was 54, etc. all the way down. You can see that. The red line is actually a percentage, cumulative percentage, and basically what we're going to do is we're going to look at the bottom of the chart again, and we can see that too long is approximately 65%. That red point is referenced from the percent scale on the right of the chart. So if we look at that red point, we slide over, it corresponds to the 65%. The bad print added another 16%, 15.9, approximately 16%. So that is 16% higher than where we were at the 65, and now you can see that we're closer to 80%. So that red dot above the bad print now corresponds over to 80. So each corresponding percentage for each of these particular defects makes that red line get higher and higher towards that 100%. And again, the red line is referenced to the axis on the right, and that 0, 20, 40, 60, 80%. With a Pareto, the Pareto principle follows the 80-20 rule, which means what we're really trying to do is identify the top 80% of our pain, and generally that comes from 20% of our issues. So 20% of our problems relate to, 80% of our problems relate to 20% of the issues. Okay, so in other words, too long and bad print, you can see that those are just over 80%. Those two are, in this case, it's 2 out of 6. So they're approximately 1/3 of our issues. So 1/3 of our issues make up 80% of our problems. Those are the two that we're going to want to address to significantly enhance our performance. We're not going to work on bad connection and missing parts. That doesn't make a lot of sense. We're going to work on the biggest problems, and those biggest problems are called our significant few. A lot of the smaller bars on the left we're going to consider our insignificant many. So we have the significant few that we want to work on, and we don't want to get bogged down with the insignificant many. Here's another example of a Pareto chart. And again, you've got not only the bars rising from the bottom that correspond to the counts on the left and that axis, the red bar rising from the or corresponding to the percentages on the right side of the chart. You can see a table below, and again, very similar percentages in some cases. In this particular example, a lot of the insignificant points, insignificant defects were summed up and included in the other chart. So in this particular case, I'm going to say that the bottom three, the scrap, the unconnected wire, and the missing studs, those three were combined in the other category and kind of grouped together. There's different philosophy on when you do that. As far as I'm concerned, in this particular example, this was fine because it actually showed it on the left. I don't want to be concerned with all those smaller ones. I don't need this chart to be 5 inches wider to the right, showing all those little onesies and twosies. What I really care about and what a Pareto is going to do is it's going to get me to the top issues. So missing screws doesn't take a rocket scientist to figure out. If I'm going to address one problem here, I'm going to go after the missing screws. How do we create a Pareto? You simply, in Excel, if you list out your defects and your counts of defects, you're going to be able to generate a column chart, and a column chart will provide you with a Pareto. You want to have previously sorted your defects from the highest counts to the lowest counts prior to generating the Pareto chart. This is a Pareto chart that you will see afterwards. We will also supply you with a Excel sheet, Excel file with a Pareto with a cumulative line on it as well, and there will be formulas in there that you can see. This is not an Excel class, so we're not going to get into how do you create those formulas, those cumulative lines, and the sum of those cumulatives. We're going to leave the formulas in there. If you have any questions, you should contact someone that can explain some of those Excel formulas to you. You don't have to use Excel. You can use other formulas too to create these. So a cause and effect diagram will be another visual tool that we can use that will provide information for problem solving and helping teams get to where they need to get to. You can use these, create these by hand. There's a lot of different software packages that can help them create them, and I think some of the more simpler ones are going to be shown in the next couple slides, and there's going to be some easy ways to remember about how to pull these together. One of the things I will tell you is that I kind of like the term living document for some of these, because they can be added to and deleted from as you deem appropriate. So it's nice to be able to have documents such as this that you can again continue to enhance as you find other things or discover different things about your process. One of the things I will tell you, and this last note here about gaps or potential missing inputs, we'll discuss that over the next couple slides as well. So here's our basic cause and effect diagram. It's also referred to as the Ishikawa diagram over the gentleman who created this. and I drew a little fish around this. It's also been known as a fishbone diagram because basically you've got these little bones that come off the fish, and then there's other bones that can come off there too, other segments relative to some of the specific items to each one of these different inputs. So in this particular case, you've probably seen the components of variation in the white belt program. Now we're talking about these components of variation being in a cause and effect diagram or cause and effect relationship. How do we remember the 6 inputs to a cause and effect diagram? Those 6 inputs are the 5 M's and the 1 E. So we've got measurement, manpower, materials, machine, and method. And then lastly, we have the E as environment. And kind of slipped there for a sec. I'm thinking the 6 M's, some people refer to environment as Mother Nature. So just another way to look at it. So when we put together our cause and effect diagram, we're going to at least start with these 6 different categories. As we brainstorm those categories, you can start to see that we're going to pull different information and different inputs into each of these categories. Now, across the top, we see method and material. We have personnel. Personnel, some people don't like to use the term manpower. In this particular example, they went with personnel, took away the man. Relative to personnel, for this changeover downtime, which is their effect, they have shortages of personnel and training of personnel. For each one of those, they have causes of the shortages. They have call-outs, they have vacations, looks like breakdowns and dual changeovers would create shortages of personnel. So for every one of these major categories, there are subcategories and then sub-subcategories, and you can start to see how this really can get into a lot of detail. What's nice is that when you're all done and you look back, you can start to think, where am I going to focus my attention? And in this particular case, there's 2 different groups or 2 different lines that had to be expanded for material and 2 different lines that had to be expanded for machines. So those looks like if I had to focus on 2 areas, the material and the machines are creating the most opportunities for variation in this particular process. The one thing I will say is, if I've only got 2 lines off of personnel, maybe we need to think about that a little bit more. Did we miss anything there? So as you're reviewing a cause and effect diagram, consider some items that may be missing from your cause and effect diagram, and gaps in a diagram may simply be that there are no more variables in that particular category. But again, it's something that doesn't look right. Question it. If your questions are satisfactorily answered, you move on. So here's a histogram which looks an awful lot like a bell curve. All right, it's not always going to look like a bell curve, but when the data is normally distributed, it's going to represent a bell curve, which represents our normal distribution. So a histogram, some people confuse this with a Pareto. This is not a Pareto. This actually is taking variables data, like a chemical analysis. These are the different analysis values that we're getting, and it's simply showing the frequency of those values in a graphical format. A Pareto will take attribute data, and the height of that will be the height of those bars will be represented by the frequency. So again, slightly different charts. They in some cases look the same. What a histogram is going to do is it's going to show us how widely spread the data is. And this is not over time. This is a flashpoint. And I'm going to take this opportunity to tell you that in addition to this being the histogram of a chemical analysis, I'd want to have a little bit more information on my graph here. And I will also tell you that whether it's a Pareto chart or any other graphical representation of data, you should have a date of your process. And if this is, or a date range, I should say, of your process, you certainly want to have that conveyed here. So this is a chemical analysis. Okay, what's the chemical analysis? What's the chemical? What line is it off of? And is this from 2012? Is this from March of 2012? Is this from the decade of 2010 through back to 2001? Where is this data coming from? That should be on the title block of this and all of the other graphs that you're representing. We don't want to have those questions being asked as you present data. The data and the information that you're presenting should include all of that. I removed some of those headers because I'm trying to keep this a lot of this data confidential. So that being said, a histogram is the spread of data in a group by the specific values. And in this particular case, along the bottom you see 20, 30, 40, 50. Those different analysis that you see there that was performed on this, the bar that say is above 30, there's approximately maybe 16 or 17 times we had values within that range. And that range is most likely down to 28.5 and up to 31.5. So it's a range of several different values. It's not exactly 30 values. It could be 30.1, 31, 31.3. So whatever chemical analysis we got, it's actually a range of values there. And you can see that there's approximately 5 or 6 categories for every 10 readings of the analysis that we have widthwise. So whether this was a percent chemical analysis or just an actual reading, there are, again, for every 10 of those, there are 6 different categories widthwise. That will be created automatically from the software that you are using. In this case, the software is Minitab. So our histogram is basically describing data, and that data is going to be for either a set period of time that we're going to need to describe. It's going to be for a particular process or product characteristic, whether it's a feature dimension on that product. It's also could be the time that product goes through your area, or a report gets time it takes for reports to get processed through your area, or invoices, or some sort of requisition. And the times could be across the bottom part of your chart, and the frequency of each one of those would create that histogram. We want to identify machines or personnel associated with that, maybe first shift, second shift, or third shift. So histograms are going to be specific to your particular process. There's different ways it can be shown, and we're going to show you a dot plot in a sec, which looks very similar to a histogram. We'll also show you another histogram, and then we'll impose the normal curve or the normal distribution and see what that looks like relative to these charts. So here's a dot plot. In this particular case, we had 150 readings here, samples that were represented by these dots. In this particular case, we can see that we've got a pretty wide spread of values, and in this particular case, these dots represent specific values. So I want to say that these were in quarter mil increments as we went across, and that was the software that generated this chart just happened to grab that. So dot plots will be per a particular set of values as well. Here's a histogram, and again, I keep thinking that there's no title blocks on these as you're creating histograms and Paretos and all. Again, I'm going to tell you, you need to have the date range, Where does this data come from? This is wonderful. This is thickness. It's thickness of what? Is it thickness of plating? Is it thickness of solder mask? Is it thickness of some sort of uh, you know part? What is this thickness that we're talking about here? So we certainly want to include all that information. What line is it coming from? What process? If you're presenting work within your company, you certainly don't need to list your company name, but certainly the characteristic needs to be identified. Again, the heights of each of these bars correspond to the frequency on the left side of the left axis, the frequency. The thickness is across the bottom. So in this particular case, thickness is around 14. We're looks like one instance there. This relates back again to the dot plot. So if you go back in the data, you can actually see where you would have had one dot there. For the 16, you would have had 2. For 17, you would have, it looks like 6. Same thing with 18, etc. So that's how you interpret this data, this chart. Looks relatively normal, and there's statistical tests that we could run to see if that's the case. You'll learn about that as you go through your Greenbelt training. So the next thing that we want to talk about here is a scatter plot. And a scatter plot is going to take two different variables, and it's going to see if there's a relationship between those two variables. So in this particular case, there's a pulse rate here and there's an age. And we want to see if there's a correlation, a relationship between the pulse and the age. So if they were to line up perfectly on each other and form a straight line, we would say we had a perfect correlation. When the dots don't exactly line up in a straight line, we still could potentially have a relationship, but it's not as strong of a relationship. So in this particular case, there's other factors that are affecting the pulse. It's just not the age. There's some other things that are affecting the pulse rate. So as we look at this data, we'd still say that there's a pretty strong correlation here between pulse and age. So as the age goes up, I'm expecting the pulse rate to go up. One thing I will caution you is that as you try to interpret data, I would caution you not to look and make assumptions or predictions outside of this test and this test area, this test window, if you will. If, in other words, if I was to ask you what would you expect the pulse rate of someone that was 70 years old, I wouldn't expect you to kind of keep this graph going up and predict something around 110 for a pulse rate. Okay, this thing, we don't know how it's going to react outside of this window area. At 60, it may start to curve back down. We don't know. So again, don't make predictions outside of your test area. Here's a particular relationship where there is no correlation. We're trying to see, does the oven temperature and the hardness, is there any type of correlation between that? So when we had a hardness of 120, what were we setting our oven at? And you can see that, we could set it high, we could set our oven temp low, and regardless of that, it appears that our hardness at the very end is not going to have, it's not going to really be affected by that oven temperature. So in this particular case, there is no relationship here between oven temperature and hardness. Here is thickness and pressure. Again, looks like a very strong relationship. This is approaching what appears to be a straight line. These points that appear to be going up to the right, that's what we consider a positive relationship. These points could also be coming from the top to the bottom and angling down. That would be a negative relationship. Okay, so we've got positive and negative relationships. You can have a positive strong relationship, or you could have a positive negative relationship. So in this particular case, it's a strong positive relationship. As one goes up, the other one goes up. This is we're going to consider a moderate relationship. There is some sort of relationship here between these two. This is actual readings between a customer and a QC department, um, and we found out that there was a relationship, but it wasn't as strong as we would have liked to have seen. And we found out that there was actually problems both with the way the internal QC department was doing things and the customer. So neither one of their processes was optimum, and we actually took the opportunity here to enhance both of those processes after we started to compare the results of both of those. So you can compare different things. In this particular case, this was two quality departments that we compared information from.